Professor Gerd Gigerenzer.
How to make good decisions. If you open a book on rational choice, you will find the following answer. Yeah? Survey all alternatives, list all consequences, estimate the probabilities, the utilities, and make the calculation. This is a wonderful mathematical theory, but it doesn't describe how most people make decisions. Do you do it this way? And it also doesn't describe how even those make decisions who write these books. As the following story illustrates, a professor from Columbia University had an offer from a rival university, and he could not make up his mind whether to leave, stay, accept, reject. A colleague took him aside and said, "What's your problem? Just maximize your expected utility. That's what you always teach your students." Exasperated, the professor answered, "Come on, this is serious." I would like to introduce you today to our research at the Max Planck Institute on a taboo topic. The taboo topic is about how do people make decisions under uncertainty, that is, when optimization is out of reach. So I start with the basic distinction between risk and uncertainty. So, almost all of neoclassical economics, behavioral economics, neuroeconomics studies decision under risk. That is, when all alternatives, all consequences, and all probability distributions are known. Even those who criticize neoclassical economics to get it wrong and say that people are not up to that still accept the same norms. What I will talk today is about a different vision to understand how people make decisions and also should make decisions. And that's about uncertainty, without reducing, with all these ingenious tricks, uncertainty again to risk. And many people are very good on that. So, I will talk about 4 points. First, in a world of uncertainty, that is, where not all alternatives, not all consequences, not all probabilities are known, and optimization is out of reach, the best decision is not the same as the best decision under risk. And we have seen in the recent financial crisis some examples where you took measures like value at risk in a world of uncertainty, and then that caused the problem rather than being a solution. Second, heuristics are one tool, and one important tool in order to deal with the world of uncertainty. And heuristics are not the product of a flawed mental system. That's what you usually hear in behavioral economics. That only appears to you if you look at problems at risk. Of course, in the risk, do your calculation, do it, yeah? And heuristics are second best, but that doesn't hold in a world of uncertainty. Third point, simplicity. In a world of uncertainty, complex problems do not always require complex solutions. And I will give you some examples. Finally, less is more. More information, more time, more computation is not always better. The reason behind that can be formulated mathematically, and I will give you some reasons for it. It's basically robustness. You need something that works in an uncertain future and not something that is optimal in the past. Let me start with a key example that Milton Friedman and Jimmy Savage used in order to both link economics to physics and to as if. It's the billiard example. Friedman argued that now an experienced billiard player will do probably whatever he does doesn't matter. We just assume that he would reason or behave as if he would use the laws of physics, and then we make the prediction. Is that a good idea? Let me change from billiard to baseball or cricket or any game where balls come in high. How does an outfielder know where to run to catch a ball? If you interview outfielders, then you get intuition. And it's intuition. It's knowing, but not knowing why. So how does it work? Richard Dawkins had the same idea as Milton Friedman. Now, the baseball player behaves as if he would unconsciously calculate the trajectory. Have you ever calculated a trajectory? So here is what you do. Here's the as-if model. So the set of x means the height of the ball at distance x is a consequence of a number of variables, including the initial angle alpha, the mass of the ball, g gravity, beta is friction, and v is the initial velocity, and so on. Now that would be the equivalent to Friedman's example. Behavioral economists might come and point smartly out, that's not realistic, you forgot about wind and spin. So what would you do? You insert that into the equation, make it more complex. And then you get something equivalent to prospect theory or inequity aversion theory. Lots of free parameters to work with. Now, what I will argue is that what actual outfielders do has nothing to do with these calculations, consciously or unconsciously. A number of experiments shows that experienced players use heuristics, several. Here's the simplest one, which works when the ball is already high up. And it has 3 building blocks. The first is fix your gaze on the ball. Second is start running. Third, adjust your running speed so that the angle of gaze remains constant. This player does exactly that. He is running and tries to keep the angle of gaze constant, and then it's there where the ball comes down. Do you want to see it again? The point is that this player can ignore all variables in the as-if model. None of them is relevant. And it's a heuristic that has the characteristics of many heuristics. It just looks at one important thing, and it does the work, the one important thing, and it's not in the equation. Now, that's an illustration. Now, one could argue, but I don't care about how actual people make decisions because I just do as-if and predict well. Are these predictions well? Now, I'll show you 2 models, the as-if model and the gaze heuristic. And I'll show you 3 predictions about behavior, not about process, that the gaze heuristic gets right and implies, and the as-if model doesn't get. The first one is, now, the as-if model would assume that you would just run to the point where you computed somehow that the ball comes down and wait there and do last adjustment. The gaze heuristic has a total different prediction about behavior. You need to move all the time to adjust. So you will catch the ball while running, and that's what the empirical evidence is. Second, the as-if model might think you run a straight line, but in reality, the heuristic implies, I'm not showing that here, that sometimes you run in a slight arc, and that's what you find, both in outfielders and dogs who use the same heuristic. And finally, somehow you would think that experts know where the ball is coming down, but they don't. And the point is, you don't need to know this because you use a heuristic that's a totally different process. And by the way, even the goal is different. The goal is not compute the landing point, but catch the ball. So here's one illustration. The same heuristic is not just used unconsciously, but it can be used consciously. Remember the miracle of the Hudson River? The 2 pilots were in the following situation. A flock of Canadian geese silenced both engines, and they were sailing, and they're trying to get back to LaGuardia, the airport. And they had to make an important decision. Will we make it? What did they do? Did they do a calculation? No, they used the same heuristic. So if you fixate your eye now on the tower, and the tower now in your windshield moves slightly up there, you're not going to make it. See that? And that's what co-pilot Jeffrey Sculls exactly tells us. The point here is, the general point, heuristics are not just part of the so-called unconscious or system 1 or whatever. You can use every heuristic we have studied consciously or unconsciously. You can train people to do that. And that's what many air companies do. So, second example, as I mentioned before, there's good evidence that the error to use models that are made for risk and apply them in an uncertain world like the real world of finance is part of the problem. I'll give you a second illustration for a heuristic, and then I go to the general case. Assume you have money, you want to invest it, you don't want to put everything in a basket, but diversify. How? Harry Markowitz got the Bank of Sweden Nobel Prize for the solution, the mean variance model. When Markowitz himself made his investment for the time after his retirement, he used his optimization model. So we think, no, he didn't. He used a simple heuristic, divide equally. It's also called 1 over n. If you have two options, 50-50. If you have three, a third, and so on. So now there are behavioral economists who make fun out of people using 1 over n. But the fun is correct if that would be a world of known risk, but not necessarily in a world of uncertainty. So there are now, the real question is, can we show which one of the two does better on some criteria? And if so, can we analyze why? So in one study by De Miguel, the 1 over n was compared to mean variance. And so there were many investment problems, like 10 American industry funds. And the mean variance model needs data to estimate its parameter. There were 10 years data. What was the result? 1 over n made more money on common finance criteria than mean variance. And another dozen of modern Bayesian, non-Bayesian models was tested. None of these could consistently outperform the simple heuristic. The important question is now the following. So my point is not, as I often been understood, to show that simple is always better. That's not the case. The real question is one which we call a question of ecological rationality. Can we identify features of the world where we can show that the heuristic does better or worse? And here are some hypotheses for when 1 over n would do better than mean variance. One is if the predictive uncertainty is large, and that's the case with stocks. Second, if n is large, the reason is clear, because the optimization model needs to estimate more parameters and there's more error. And finally, if the learning sample is small. In that case, it was 10 years. And then one can, by means of computer simulation, for instance, answer the following question. So if you have 50 assets, how many years of stock data would you need in order so that 1 over n, all these calculations pay? The best answer is 500 years. So in the year 2500, calculate. So follow your intuitions. Do banks understand that? I'll show you what I got from my own internet bank. I translate. It says, with Nobel Prize winning strategy to success in investment. And then the question was in this letter, do you know Harry Markowitz? No. Then you should know. And the letter tells the story that he won the Nobel Prize. And the bank does this, and there is a warning against your own intuition. What this bank has not understood is that they sent the letter 500 years too early. This is not just a one shot here. What I show you here is 20 studies of this kind, economic, psychological, biological study. The point is, in these studies, is the difference between data fitting and prediction. If you know already your data, you do better with complex models. But as you see, the complex model is your multiple regression. You see the crossover. There are two heuristics that do better in prediction. This is cross-validation here. One just goes with one good reason, and the other one is 1 over n. It just throws away all beta weights. And there is also a heuristic that is too simple. This is called a minimalist, just takes any q randomly, and that's not good enough. So the general idea is now to dare a science of heuristics, to dare to ask the question, how do people make judgments when not everything is known? And So we try to answer three questions. One is, what's in the adaptive toolbox? So there's not one tool, not one maximizing tool, but several. So not everyone appears with a hammer, nail, but there are a number of heuristics. Second, in what situation is the use of a heuristic normative, prescriptive? In the good old days, nobody asked a question about heuristics in a prescriptive way because they were always considered second best, but that's not the case. Third, intuitive design. We use the knowledge and the results here in order to help doctors and other experts to make better decisions. I'll just give you a quick overview about the studies on types of heuristics we are working. You've seen tracking, gaze heuristics. You got something about equal division. I just mentioned one. So one of these are evolved capacities of the human mind, like the ability to recognition, to track, and such things that heuristics exploit, which a pure mathematical formula cannot exploit. And trust is one of the means that works in many of these heuristics. For instance, one is you go to your doctor, do you ask questions? Some just trust your doctor. If the doctor tells you take a PSA test, prostate cancer early detection, you take it. Most economists do this. We've studied economists, and in front of the doctor, 2/3 say that they just followed whatever the doctor said. They didn't even know the pros and cons, so they couldn't weigh them. And so then the question would be, in what situation is a heuristic like trust your doctor a good one and one not? And here are three conditions that all should hold. If the doctors know the medical evidence, if the doctors have no conflicts of interest, and if the doctors don't practice defensive medicine. None of them holds generally in the US. So you have to think yourself. And finally, I want to make my last point, and this is the deeper understanding why less can be more. Okay. The classic account about why heuristic in famous articles from Konslik to others is you use a heuristic because of the accuracy effort trade-off. You have less effort and you trade off a little bit accuracy. This is true in a world of risk. It is not true, not generally true in a world of uncertainty. As you have seen already, you can have both. You can have a simpler heuristic and a more accurate result. And the real trade-off is another mathematical trade-off. It's between bias and variance. I'll be brief, but if you get this one, then you got quite a step forward. The total error consists of three. This is now about prediction, consists of three. Noise, the measurement error, which we can't deal with. Then bias. Bias is if you, for instance, if the truth is a polynomial and you have a linear equation, you have a bias. You just don't get it. Variance is the one that's usually overlooked. What is this? Variance you get if you do parameter estimation. And for instance, if you have many different samples, every time you get a different solution, a different curve. And the variance between these curves is the error. 1/n has no variance because it always gives you the same thing, but it may have a strong bias. Mean variance will have both bias and variance. And I'll show you now in an example how that works. You have the temperature in London. These are average temperature per day, 365 points. And you think there could be other indices, economic indices. And you want to know what the underlying structure is. And here you have two polynomials, a 12-degree and a 3-degree. Which one has the better fit? Now, 12-degree. And in general, here you have the error on the y-axis, and lower is better. The more complicated the model is, the higher degree polynomial, the better the fit. And if you're mathematically sophisticated, you know with 364, you have a zero, no error anymore. But that's not the goal of science. The goal is prediction. How, if we now predict next year's temperature with each of these models, will it still be the case that the most complicated, the best fit, will be the best one in prediction? How will this curve look like? I'll show you. It's U-shaped. Too simple. Now, a 1-degree polynomial is a line. Is not good enough. Huh? And you already get the lowest error around 3 or 4. Huh? But then it goes up. So too complex, a too good fit is not good. And here you see the idea of less is more. There is a point where more is not better, although it looks so in terms of fitting. So let me summarize. I talked about a taboo topic, decision-making under uncertainty. And I was trying to make the following points. The best decisions under risk are not the best decisions under uncertainty. We need to study that and not just think that the models we have now translate. Second, heuristics are not second best. They are not the strange quirks of our minds, but we need them. There's a reason why we have them and also why animals have them, because we live most of the time in an uncertain world. We're not playing lotteries in casinos all the time. Finally, simplicity. Complex problems don't require complex solutions. There's a reason for this. The bias variance dilemma is one of the reasons. You need to find something robust, not something optimal, because there is no optimization in an uncertain world by definition. And finally, less can often be more. More information, more time, more computation does not generally lead to better decisions. Thank you for your time and attention.